My name is Eric Ostergaard. I am a Senior Application Engineer with HBM Francia, and I will be presenting today's topic titled Frequency Domain Fatigue Analysis with nCode DesignLife. Before we proceed with today's main topic, I'd like to give a brief description of who we are. HBM Francia is an engineering software company made up of two software brands, nCode and ReliSoft. In addition to the software, we provide conceptual, theoretical, and application-based training on all of our products. We also provide professional services in the form of materials testing in our own testing lab, solutions for design, development, testing, and also solutions for asset management. Our software portfolio contains numerous tools within both ReliSoft and nCode. The first column contains a number of tools for reliability analysis. This includes tools like Weld for life data analysis and BlockSim for system modeling. The second column includes tools like XFMEA and XFracus for reliability management. And the final column contains nCode tools. Tools like GlyphWorks for test data analysis and VibeSys for acoustic and vibration analysis. However, the focus of today's webinar will be predictive fatigue analysis on FE results with nCode DesignLife. So our agenda is pretty straightforward. What I'd like to do is share with you an introduction to vibration fatigue, and that's going to be followed by 3 steps. Each one of these steps is going to contain a demonstration. So we'll go over single-axis random excitations. We'll then proceed to the next step, which is multi-axis sequential random excitation, followed up by multi-axis simultaneous random excitations. At the end, we'll get to cover advanced features of vibration fatigue, and we'll wrap things up at the end with a summary. All right, let's take a look at the introduction to fatigue. So if you've ever sat in on an nCode webinar or one of our training classes, you've probably seen this slide before. It is what we call a fatigue analysis roadmap. And essentially, this represents how a fatigue analysis is going to be done. It doesn't matter if it's done with software or with pen and paper. You're going to be following this type of a roadmap for your fatigue calculations. Now, the first 3 boxes are all inputs, and the specifics of these inputs for vibration fatigue will be the focus of the first section we're going to cover here. Now, for materials, if you've done something like this before, that's not going to be very different. We're either going to be using fatigue properties defined by a stress life or strain life methodology. Our loading, however, is going to be a little bit different. If you've done design life analysis or even strain gauge fatigue calculations in GlyphWorks, you're probably more accustomed to doing time series based fatigue calculations. In the examples that we'll see here, it's going to be described in the frequency domain. Lastly, the structural response for DesignLife, this is essentially your FE results. And again, if you've done something like this before, you've probably done a linear analysis, a linear static analysis in FE and brought those results into DesignLife. And what we will be doing here is actually a frequency response analysis in FE. Therefore, we're going to have real and imaginary stress results across a range of frequencies. And that is going to be paired up ultimately with our loading that's also described in the frequency domain. Now, when we combine all 3 of those inputs, we're going to perform our fatigue analysis. We're going to be using rules that we've seen before, like Miner's rule for damage accumulation. We're going to apply that to our fatigue curve. And ultimately, we can then express our results at the end, either in the terms of total damage or the inverse of that, life. So life just being defined as 1 over damage. Now, because we're focusing on vibration fatigue, we need to take the structural response into consideration when we consider our loading. For example, when we develop a test for structures that do not respond dynamically, the quasi-static branch, the upper branch that we see here, we can use lab tests like constant amplitude and block cycle loading. Now, these are simplified representations of cyclic loads in the time domain. They are going to have some sort of equivalence to damage based on a real-world event. but the frequency of those cycles is really not going to have any impact on the response or the damage that that part would see. However, if we need to make other choices, we need to make other choices if our structure is going to respond dynamically. If our loading is transient and the response is dynamic, the test should probably be run in the time domain. However, if the loading is steady state and the response is dynamic, we can run the test in the frequency domain. We've got two options on the slide here. They aren't the only options, a sine sweep and a random PSD. They're just two examples, and in the demonstrations that you'll see throughout the webinar today, we're going to be using random as an example. However, they can easily be interchanged. All right, so let's talk a little bit more about a need for dynamic analysis. On occasions, loads will cause a structure to respond dynamically, and the resonance that occurs can greatly increase the displacement and stresses throughout the structure. These increased displacements and stresses can be far greater than if we had made static assumptions. And these high levels of stress are really what's going to be driving fatigue. Therefore, it's really, really important. We have to be careful when we determine if our structure is responding statically or dynamically, and then apply the correct methodologies in FE to be able to capture those dynamic effects if it's necessary. Now, in nCode DesignLife, there are two possibilities for dynamic fatigue analysis. The first one is a modal superposition. It's going to be performed in the time domain, and it works well for transient events. The second one is the frequency response analysis. This one will be done in the frequency domain, and it works very well for steady state events. And that is, in fact, the focus of today's webinar. So I want to cover with you three different steady state cases. We're going to start with harmonic vibration fatigue. In this one, it's typically applied to loads that we might see caused by rotating machinery. Examples of this would be engines or turbines. And the two different options we have here are if you were performing something like an engine run-up, where we're simply sweeping through a range of RPMs. A really good way to describe the loads that might produce, maybe on a bracketed part, for example, is a sine sweep. And if we had an application where the engine was run at a fixed RPM, or constant RPM, something like a generator, we might choose to use something like a sine dwell. So both of those harmonic vibration fatigue cases are going to be really good representations for those types of applications. The second case is going to be the random vibration fatigue. So with random vibration, we're typically trying to describe things like road loads, road profiles, wind loads, wave loads. The components that we have could potentially be exposed to these types of vibrations for a very long period of time. It could be on the order of hours or sometimes years. And the time series event, which we see down below, is often going to be represented as a power spectral density, or a PSD, which we see in the upper right corner. Now, when describing the time series event with a PSD, it's necessary to describe the distribution of cycles. As I mentioned earlier, it's often impractical to measure or analyze data of an extremely long time series event. So one must consider a few challenges that we might have. Imagine that extremely long time series event, and you sample just a small portion of that event and measure it in the time domain. You're going to have some questions. The first question that might come to mind is what duration is necessary for that small sample period to be statistically representative of the entire event. Another problem you might run into is you could make multiple sample measurements of that time series event. They may even, just to simplify things, may even be of the same duration. And you can perform fatigue calculations, and it's entirely possible that the damage results might be different. So how do you handle two separate measurements of something that should essentially be a randomized event and getting two different answers? The plot that we see down below shows a 2D histogram, which might shed a little bit of light in terms of what we're trying to accomplish with vibration fatigue and the distribution of cycles. So the first thing that we see is horizontal axis of the range of cycles, so basically the size of the cycles. And on the vertical axis, we see the count. So our 2D histogram in red showing us the cycles that would have been observed if we had measured that data for a short period of time, in this case 10 seconds. It seems as if we're starting to characterize some of the smaller cycles fairly well. We've got a trend that is appearing, and those cycles are occurring relatively frequently. But as we get out to the right end of this plot right here, we're starting to see some gaps appear. So we simply have not sampled the data long enough to capture some of those larger cycles that might be infrequent. So naturally, the next step might be, well, let's just increase the duration of our measurement, and we could increase it to 100 seconds. Again, those lower range cycles, they're starting to agree fairly well in both of those measurements, and we're starting to fill in some of the gaps out in the larger cycle range. However, we still have some gaps. So then we increase the sample measurement for even longer, so we measured for 1,000 seconds. What we now have is a much better representation of all the cycles, small to large, and being able to quantify the count. Now, what vibration analysis allows us to do is consider a statistical distribution of those cycles. There's several different models we can choose from in the software, but effectively, it's going to show something like this dotted black line that gives us a nice distribution of those cycles from a statistical perspective. Now, the third case is a combination of the first two. We are looking now at sign-on-random vibration fatigue. A common example of this might be a test spec from the MIL 810 handbook. And what we can see in the plot below is that we have in red a random PSD. So that is representing all the noise that our part might be subjected to. And then also we have a number of blue lines on the plot that are showing us when we might have some sine tones. Now, a really common use case for this is a helicopter. If you can imagine the loads that the airframe of a helicopter is subjected to, there is a lot of noise. It can be described as random noise. So that's going to be the PSD portion that we've got in this example. But there's also some very significant sine tones that might be caused by, let's say, the main rotor rotating at a fairly constant RPM. And those are simply going to be sine tones that overlay on top of the random noise. Now, when we talk about defining the vibrations as a loading input, we've got a number of different ways in which we can bring this into the software. Probably one of the easiest ways to do this is with the vibration generator glyph. If you were to drag this glyph out onto the workspace and look at its properties, you'll see that under the different types of vibration loads you can create, we'll see a drop-down menu that contains random PSDs, sine sweeps, sine dwell, sine on random. Depending upon the one that you choose, you then have the ability to fill out a user-defined table that would then perhaps describe the breakpoints that you have in your random PSD. And that can then be piped as histogram data into your vibration fatigue analysis glyph. We'll see that in a little bit. Alternatively, we can also use multi-column data. So that's, if you've used GlyphWorks before or nCode DesignLife, that's going to be a yellowish colored pad. And it effectively describes the same type of information, but the source of that information may have come from a text file or an Excel spreadsheet or something like that. Now, the inputs into the fatigue roadmap for structural response is going to be your FE results. As I said earlier, we're going to be, in most cases, looking at a frequency response analysis. So we're going to have real and imaginary components. Depending upon the FE tool that you're using, they call that slightly different things. For example, ANSYS uses the terminology harmonic analysis. In Nastran, you would be running something like a solution 111. But in all cases, there are some considerations we need to take into account. The first one is that we need to apply a unit excitation in FE, and that needs to match the excitation units of the loading. So for example, if your PSD that represents your loading is in units of G squared per hertz, in FE what we need to do is we need to apply a 1G excitation across all the frequencies that we're going to be solving solutions for. In addition to the frequency response analysis, we can include static offset load cases. These static offsets can represent things like gravitational effects. It could be inflation pressures or maybe stresses due to assembly loads. Essentially, some type of stress that is not going to be changing. It is static, and that is then going to be applied as a mean offset to the cyclic component that's coming from the frequency response analysis. Down below in the table, you'll see a number of different solutions that you can call for depending upon your FE tool that you're using. So that's probably just going to be a good reference for you to come back to later on if you are ever in doubt as to what you need to request in the different FE tools. The final input into the fatigue roadmap is going to be the material definition. So if you've ever used nCode before, you've probably seen that it comes with several material libraries. And these libraries, for the most part, contain fatigue curves, sometimes stress life, sometimes strain life, sometimes both. And those can all be accessed through the material manager. Now, it's important to know that these libraries are user definable. So if you have your own materials, you have the ability to add those to these libraries and then use them in your analysis. And as I mentioned earlier, for vibration fatigue, we have the ability to use either the stress life or the strain life material definition. All right, now that we've covered the inputs into our fatigue roadmap, what I'd like to do now is talk a little bit about single-axis random excitation, and then we'll talk also about multi-axis sequential random excitation. And there's going to be a demonstration for both of those. So to get started, what I want to show you is a process that is a bit more specific to vibration fatigue, and in this case from a single input. And this roughly matches the roadmap that we saw earlier. The FRF that I'm circling right here with my mouse, this is essentially your FE solution, your frequency response analysis. That's coming from FE. And then down below, if we are talking about a random loading, we would be representing that with a PSD. Now, the two of these can be combined using the equation that we see above. In fact, it's the same equation that we see right here. And the result of that combination is going to be a local stress PSD. So we're going to see a response PSD on every entity on our FE model. Now, when we look at the cycle distribution of the response PSD, we can use counting methods like Lalonde and Durlick, or perhaps narrowband, to come up with our cycle histogram. And we can see a sample of that right here. Once we have this cycle distribution, we can apply those cycles to an SN or an EN curve, much like we would any other type of fatigue analysis. So basically, from here on, it's going to be a very similar process to any other kind of fatigue analysis we've done, even if it had been done in the time domain. And then ultimately, we can express our results right here in terms of damage or life. So what I want to do for you now is actually navigate to nCode and show you a demonstration of single-axis random excitation. And what I'll do is I'm going to build from scratch this process. I'm just going to talk through each glyph and talk about some of the important aspects as I build this for you. Let me just switch over to nCode. And give me just 1 second here. All right, so what I'm going to do is navigate, or actually have already navigated to some sample data. What I'm going to be using is worked example number 10 in DesignLife. So any of you who have nCode already, these are sample models that you can use. And in fact, there are step-by-step instructions underneath of the manual section here on DesignLife that you could follow on your own if you wanted to try and repeat this analysis. So the first thing I'm going to do in my available data window is navigate to an FE model, and I have, if I make this a bit wider, we'll see the full name, a bracket that has been solved in Nastran. It's an OP2 file. I'm going to drag that out onto my workspace. And if we just take a look at this, let me enlarge it for you. We have a bracket that has a number of solutions already solved on it, and let's take a look at those. In the properties under the FE display, let's enlarge this dialog box so we can see the full name. On the result cases, you will see that I have a number of solutions in the X direction. These all happen to be solved at 10 Hertz increments, going all the way up to 500 Hertz. And as soon as those are done, we then start back up in the Y direction, 10 Hertz increments again, and then we see the Z direction. So this particular model, in fact, contains excitations in 3 different directions, but for our first demonstration, we're only going to be using one of them. We're going to focus on the Z direction. It happens to be the one that is most damaging, so it gives us the most illustrative damage contour plot. And we can then bring out a PSD, and I have an example PSD already. I'm going to be making use of this multi-column file right here. You'll see if I expand this, there's a lot of information inside this multi-column file. We have multiple PSDs as well as some cross spectrums, and we are going to ignore these for the moment, and we're focusing just on this PSD. However, I will drag the entire file out onto the workspace. That's going to show up as a multi-column input. The next thing that we need to do is navigate to the DesignLife glyph palette, and we're going to go all the way down to our vibration fatigue glyph right here, and I'm going to connect some pipes. So basically, I'm going to bring in my FE results, I'm going to bring in my loading, and if we'd like, we can display some of these things. We can display the FE results graphically. That's going to be our damage contour plot. And just so that you can see what it looks like, I'm going to place an XY display right here on my PSD. And that'll allow us to show the PSD. Now, before I hit the run button, I need to define a few properties inside of the vibration analysis glyph. And generally what I would do is navigate to the material mapping and then load mapping. But I do have, in fact, one other property to change. So I'm going to make it easier on myself and just go straight into advanced edit. And once in advanced edit, I'm going to first go to my loading. And here you can see it's already recognized all 3 directions. We've got the X, the Y, and the Z directions. And no need to be concerned that you can't see all of the other frequencies displayed for each of those directions. They've simply been condensed for easy viewing purposes. And what I want to do is make sure that I grab the Z direction. And I'm going to move that over to the right. And we can just confirm that we got the Z by making this a little wider, and we can see it has the Z direction in the title of my description. And then I want to make sure I grab the Z PSD and drag and drop that up here. So that is the mechanism that allows me to associate those 2 together. I'm now going to go to the material map. And here I'm going to just pick an aluminum alloy from one of the default libraries. If I scroll down here, you can see there are many other different materials I could have chosen. But we'll go with this aluminum alloy for now. And then that last property that I talked about that I needed to change is in the StressLife engine, and it is simply for demonstration purposes to make it run a little quicker. Instead of using critical plane for my stress combination method, I'm going to use an ABS max principle. Now we're all good. I can hit the OK button, and I can run the process. And what we will now do is convert our stress solutions here in FE due to a unit excitation along with the PSD in the Z direction into a damage contour plot. Let's enlarge this and just take a look at what we've got. We now have damage on this particular part as if it was excited in the Z direction. So if we're trying to come up with an analogy in the physical world, this would be like taking this bracket on a single axis electrodynamic shaker table and shaking it in that one single direction. Now, if you're not accustomed to looking at things in damage and you would prefer something like life instead, you simply need to go to the properties of this glyph. You can go to result type and you can select life, and it would then display graphically the inverse of damage. I'm going to go ahead and just leave it at damage for now. And let me show you one last thing, and that is the PSD. Now, remember, we had quite a few things in this multi-column file, and we're only using one of them. We're actually using this green plot right here. So one of the things we could potentially do is just show one of them. And then I'm going to use this blue arrow to index to that third channel, which is the PSD in the Z direction. This is the loading that we have applied to our frequency response results from FE. All right, what I'd like to do now is navigate back to the PowerPoint and cover one more slide, and then we'll do a demonstration on multi-axis sequential random excitations. So basically what I'm going to do is take the process that I just built, make a few modifications to the loading, the way we're describing the loading, and also there's a couple other properties that I'll walk you through as well, and show you how we can do multi-axis sequential. So this is effectively going to be a virtual shaker table where we are exciting the product for a period of time with some PSD in one direction, and then perhaps we reposition that part and shake it again for a period of time, and then reposition it a third time so that we can get the other excitation, the X, the Y, and the Z directions. All right, so let's take a look at this process that I had just built. And what I'm going to do is go back into the advanced edit of my vibration analysis glyph. And I'm going to go to vibration load. And what I need to do is I need to change this loading type to duty cycle. Duty cycle is a loading type that's going to allow me to create a sequence of other types of loads. As soon as I click this, you'll notice that the graphical interface changes a little bit. We now have a blank tree structure that I can define as a user. So I can right-click here on my duty cycle load provider, and I can add vibration load provider. So I'm just going to do this 3 times. Right here. And for illustrative purposes, I'm going to rename all of these so that we can associate them more easily when we look at the results. So I'm going to rename this one X. I'm going to rename this one Y. I'm going to rename this one Z. All right. The next step is we need to associate each one of these vibration load providers with a load case from FE to a PSD that's in my multi-column data. I'm going to right-click and edit. And now you see a dialog box that looks a lot like the vibration loading type dialog box we saw earlier. I want to grab my X direction and move it to the right and drag and drop my XPSD. So that one is now done and assigned. I'm going to do the same thing in the Y. I'm going to grab my Y direction, move it over, and drag and drop the YPSD. And then finally, I'll do the same thing in the Z direction. So we'll move the Z across, and we will drag and drop the ZPSD. Now, before I leave this slide, right, or this dialog box right here, I want to explain one thing, and that's this final column called repeat count. By default, when we associate a PSD to a load case, we are exposing that FE model with the PSD for a duration of 1 second. So if I were to go in here and change this repeat count to something other than 1, if I type in 900, for example, we would expose that part to 900 seconds of that vibration excitation in the X direction. We can do the same thing for the Y and the Z. However, just for ease, I'm going to leave all those at 1 second. So we've got 1 second exposure duration in each direction. And before I leave the advanced edit configuration, I'm going to change 2 properties. And they have to do with the way in which the results of the duty cycle are going to be displayed. So I'm going to go into the Stress Life engine, And I'm going to make sure that we output all of the event results. By default, all we see are the total damage of the whole duty cycle, and what I want to see is also the individual damage caused in each of the individual directions. So we'll set this to true. And then on our piped post processor, I want to make sure we can see them graphically, so I'm going to create a channel for each one of those events that I'm outputting. We'll see how that works in just a moment. So now that I hit the OK button, I can run the process again. And let's take a look at the results. So the first thing that we see in the upper left, we can see that this is the X direction. So we are looking at a damage contour plot representing damage caused in that X direction. And there's really not a whole lot. We have a tiny little bit of damage near the lower two holes. We have a tiny little bit of damage that's occurring kind of in the crease of this bracket. And I can use these blue arrows then to index through the other event solutions. So now we're looking at the Y direction. And in fact, the excitations in the Y were so low that we didn't produce any damage here. We've got a threshold that's been established for extremely small cycles, and we just return 0 damage. And then finally, we see the Z direction. And the damage contour we're looking at here is identical to what we saw the very first time when we just did a single axis excitation. And the final time, the fourth time, is going to show us all, which is a linear accumulation of the damage from each of those three events. So this is very much analogous to that example I gave you earlier about the single axis electrodynamic shaker table where we're repositioning the part and exciting each of those directions independently and sequentially. All right, let's go ahead and jump back into our PowerPoint and go on to our next section. And this is going to be our third demonstration. So we're going to talk about how we can do multi-axial simultaneous random excitations. And what I want to do is just revisit that process we saw earlier with a few additions on the input side. Now, when we saw this earlier, we had just a single frequency response from FE, and we had just a single PSD from our multi-column source. And what we're now introducing is multiple FRS. So we have perhaps an excitation in the X direction. This might be excitation in the Y direction. And we also have multiple PSDs. We have an excitation in the X and an excitation in the Y. But there's one more thing that we need to be able to capture, and that is the potential for any interaction between the excitation in the X and the Y. And that's going to be described with the CSD, or the cross power spectral densities. What we see here are some sample plots of phase and gain, and essentially what that is suggesting is at any given frequency, and let's just say at a specific frequency like 20 hertz, when we have an excitation in the X, what is the gain of that excitation for the Y, and also what is the phase? Are the two both occurring in a positive direction together, or are they out of phase and essentially might be oscillating back and forth out of phase of one another? So this does introduce a little additional complexity to our analysis, but really from a mathematical perspective, all it means is that the equation we use to calculate our local stress PSD is just a little bit longer. The original one we saw a few slides ago was just this first term right here. And now we're just going to introduce a few other terms to incorporate excitations from the other PSD as well as any interaction between the two. We can choose a statistical model to come up with a cycle distribution, and once we've gotten this cycle distribution right here, we apply that to our fatigue curve, and everything else thereafter is going to be the same. Let's take a look at a couple of slides, and then I'll build the process for you. And the first slide that I want to show you is a slide that talks about how we actually generate the PSDs and the cross-spectral densities. Now, some of you have probably already done PSDs for totally different purposes, and it's a fairly straightforward thing to do in nCode. We're going to use a tool in GlyphWorks called a frequency spectrum analysis. We'll see that in just a moment. And The cross-spectral densities are done a little bit differently. We're going to be looking at coming up with a gain and a phase of basically one PSD to the next and the next PSD to the next. So we'll have a whole bunch of pairs of cross-spectral density plots where we're looking at, let's say, X to Y and X to Z, Y to X and Y to Z, so on and so forth. In addition to those two things, and we can see them graphically right here in the displays, we're going to be generating a third file, or a second file, that has the file extension MPL. And that just stands for multiple PSD loads. And it's not a requirement to use this, but it will make your life a little bit simpler when we get into the DesignLife process and begin assigning these numerous PSDs and these numerous cross-spectral densities to the various load cases in our epi model. And then we're going to build this. We're going to, in fact, what I will do is the process that I've already built, I'm just going to make a few modifications to that and show you how easy it is to change it to being able to do a multi-axis simultaneous random excitation. Let's go ahead and go into nCode, and I'm actually going to open up a process for you in nCode. Let me just share this. This is a process that exists in work example number 10. So if you guys have nCode already, you'll have access to this process as well. Figured for the sake of time, it'd be easier just to show you with an existing process where these cross-spectral density plots come from, as well as the PSDs. And it's all going to start from some real measured time series data. What I've done effectively, if we think about the bracket that we were looking at earlier, is I have instrumented this bracket somewhere at the base in a location where I can describe the excitations going into the brackets. I'm going to be measuring them with a triaxial accelerometer so that we get X, Y, and Z excitations, and we can see those here. And we've got some time series data. Now, before I run this, I'm going to just open up this glyph right here. This is nothing more than a superglyph, which contains a number of standard glyphs inside of it. So let me just expand that. And what we see here is that my time series data will be piped into a frequency spectrum glyph. This is going to generate my PSDs. And it will also be piped into a frequency response analysis. This is what allows me to determine the phase and the gain between each of the channels of my time series data. Now, all of that is going to be going out as histogram data, and we have a couple of scripting glyphs right here too, and these are just some scripting glyphs that build the MPL file that I mentioned earlier, and we'll see how that one's going to be used in a moment. But for now, let me just run this process, and we are going to get an error message here, and that's okay. I'll explain that in just a moment. This message right here is just asking me if I want to overwrite the MPL file and the multi-column file that's actually already been created. I'm just going to say don't overwrite. It's perfectly fine. The main purpose here was just to populate these plots. So let's take a look at our PSDs. Here are the three PSDs that we've got for the X, the Y, and the Z directions. Those are all calculated independently. Here we have the cross-spectral densities. We've got gain and phase for the X versus Y. And if I use these indexing arrows, I can see X versus Z, as well as Y versus X, so on and so forth. We've got a number of those cross-spectral densities. Now, once those are created, and remember, that is really just this multi-column file plus the MPL file, we can use that directly in the DesignLife process. Let's jump back into that process that I was building earlier. And what I want to do is make some modifications to my vibration analysis glyph here so that we can do a multi-axial simultaneous analysis. Let's go back into Advanced Edit. And what we need to define is a different way in which our loading is going to be processed. So if we go back to Vibration Loading Type, and then go to this Advanced tab, you will find that there is a drop-down menu that allows me to define different loading methods. And one of the items on this drop-down menu is multi-PSD. Now, before I click away from this menu, it's worth noting that this is where you could choose different loading methods. You could use this drop-down menu if your input was defined as a sign sweep, or sign dwell, or perhaps even a sign on random. But for now, for this demonstration, we're going to select multi-PSD. And now, when I go back to my edit loading, the graphical interface is going to look a little bit different over here. What we're going to be building is a square matrix, and in this case, since we have 3 directions, it's going to be a 3 by 3 matrix. And instead of manually dragging each one of these PSDs to a box and then each one of the cross spectra to a box, I'm going to populate this automatically just by browsing to that MPL file. So that MPL file exists in the same directory where we had just run the previous process, so that's work example number 10. I'm going to click on that. And if we give it just a moment, you will see that it will populate a 3 by 3 matrix here. Sorry about that. There's the 3 by 3 matrix. And you can see that all of the PSDs, the X, the Y, and the Z, are on the diagonal, and all the cross spectra are on the off diagonals. That's exactly what we need to see there. And we should be good to run this process. So let me hit the OK button, and now hit the Run button. And now what we're looking at is the damage contour caused by all of those 3 axes having excitation at the same time, with their phases and their gains between one another being defined with the cross-spectral density plots. This plot, in fact, looks quite a lot like the Z-axis, simply because that one was so dominant, but it is entirely possible that there could be other scenarios where you have enough excitation in the other axes that this does start to look a little bit different. And in fact, it may differ from the damage that was accumulated by doing the 3 axes independent of one another, simply because you lack the interaction that might have occurred had they all been done at the same time. Let's go ahead and jump back into our PowerPoint. And what I'd like to do is cover a few advanced features and start to finish this up. So the first thing that I'd like to talk about is modal-based frequency response functions. So everything we've discussed so far has been based on performing a frequency response analysis in some FE tool. We've gotten FE solutions that are described with real and imaginary stresses and in the frequency domain. What we can do instead is a modal-based FRF. Essentially, what we can allow DesignLife to do is pair modal stresses, so we can do a modal analysis in FE, with modal coordinates that could also be done separately in FE, and then with that information generate a frequency response function inside of DesignLife. Now, the reason we might be tempted to do this is because it doesn't really take long before FE results of a frequency response analysis become extremely large in file size, and therefore they become a challenge in post-processing. It's difficult to get some of those answers in a fairly fast analysis. Additionally, we can greatly increase the resolution of the frequencies and thus get more accurate results, because that frequency resolution is going to be driven now by the frequency or the resolution that we've defined in the modal coordinates. And these modal coordinates right here, they are just multi-column files that are fairly lightweight. It's very easy for us to add data points in that to improve the resolution. So DesignLife can process those modal stresses and the coordinates that we've got listed below. So depending upon the FE tool you're using, you're going to have some different solutions that you're going to call when performing your analysis, when you do your modal stresses as well as your modal coordinates. So that table is going to be a good reference for later use. The next thing that's worth mentioning is that we can do vibration fatigue on seam welds as well as spot welds. So everything we've seen so far has been fatigue analysis in the frequency domain on parent metal. The cycle counting methods that we've seen, those can be used in vibration fatigue, and they can be applied to the stress life methods that we use for welds. If we're doing seam welds, Typically what we do is we take a structural stress-based approach, which means in FE, the solutions we're usually going to be working with are forces and moments. And those forces and moments in the weld area can be converted into structural stresses with our seam weld engines. And once we've got those structural stresses, we just apply the same methodology that we've seen in the last few slides. If we're talking about spot welds, it's fairly similar. The structural stresses from spot welds can be calculated from the results that we see below. That's going to depend on whether we're talking about spot welds that are defined as beams or ACM welds. And in either case, we're really going to be looking again at forces and moments along those elements representing the spot welds and calculating structural stresses in and around that weld area that we then use our vibration fatigue stress life methodology for. I've got a couple slides on important considerations, and the first one is extremely important, and that is regarding damping ratios. So in reality, each natural frequency that our physical parts have a corresponding damping ratio. They have a unique corresponding damping ratio. Oftentimes we assume a damping ratio, and many times it's in the lower single digits. 5% is a pretty common value that we might assign to an FE model. However, very small changes in the damping ratio can result in extremely large changes in fatigue. And the image that we have in the upper right is a perfect example of that. If we assigned a 5% damping ratio to this very simple part that we have right here, and we looked at this critical area where we're seeing a lot of damage occurring, the life might be represented as 630 hours for some PSD. If we apply that same PSD to the same model where we've changed the damping to 3%, so it's a less damped model, the life is going to be drastically shorter. The stresses in this area are going to be higher. This area right here is an area that is perhaps greatly affected by a resonance frequency. So we're seeing a large amount of displacement, which results then in a large amount of stress, and that is greatly affecting the life on that part. Now, unfortunately, the only way you can get the corresponding damping ratios for the natural frequencies is experimentally. So if you have a physical prototype, it is entirely possible to instrument that with some accelerometers so we can measure the input going into the system as well as the response in various locations. And we can perform an experimental modal analysis with tools in Glyphworks to then calculate the damping ratios for each of those natural frequencies. In addition to damping ratio, another important consideration is going to be the frequency resolution of your frequency response analysis. What is really important is that the statistical cycle distribution is based heavily on the RMS of the response PSD. So when we solve for different frequencies in FE, we want to make sure that we have represented this curve fairly well. We want to capture the peaks, and maybe clustering around those peaks might be necessary. That could be a little bit helpful in getting a good representation of the peaks. But we also want to have enough data points in between the peaks to accurately represent the valleys, thus getting a good representation of area under the curve. Now, in addition to that, we need to take into consideration the resolution of the response PSD. Now, the resolution of the response PSD can be a function of the PSD itself, the loading PSD. It can be a function of the frequency response analysis from FE. It can be a function of both of them. So that would be PSD driving the resolution of our response PSD, the frequency response driving the resolution, or perhaps both of them, having more lines coming up right here, or we could do equally spaced. Now, the recommended approach might be to do frequency response frequencies. That one's going to be relatively safe and fast. Or we can do the safest one of all. It will increase the computation time somewhat because we have more solutions that we are evaluating here. And do keep in mind that the breakpoints in our PSD, they may not line up perfectly with a solution that we've solved in FE. And therefore, if this red line right here intersects this FE, there may be some interpolation required. What I'd like to do now is just wrap some things up with some closing remarks. And the first one is just to go over applications and benefits that we have for conducting random vibration fatigue analysis in DesignLife. So if this is something that we're doing during the design phase of a structure or a part, naturally we can get accurate fatigue life predictions without having to run any kind of long transient analysis. If this is done in the qualification stage, there's a number of things that we can do. We may be running a shaker table test on a prototype, and we can actually simulate that shaker table test in DesignLife and determine what the damage might be before we even run that shaker table test. After we've run the shaker table test, we can investigate a little bit more deeply into reasons why a part might have failed. We can investigate the margins as well. And we can even use this in conjunction with some accelerated testing tools that are in GlyphWorks. So this would allow one to take an existing PSD that you might apply to a real shaker table, or maybe some time series data that you're trying to synthesize a PSD, and accelerate that test. And we can do that same acceleration in DesignLife and make sure that we're not getting into the realm where we have a too aggressive of a test that might be generating other failure modes like static failure. We can compare the damage that our part sees with standard spectra that might come from some standards like the MIL 810 handbook. And we can do things like comparing damage between different loading types. We can apply a random excitation, see what kind of damage our part would see. We can then replace that with a harmonic like a sine sweep and see if that's any different. In fact, the comparisons don't end there. We could look at the damage of a single axis versus the damage of multiple axes done sequentially to see if we can get away with a physical test that does just a single axis. You know, if the Z direction contributes to 99% of the total damage, you can greatly simplify your physical test by completely skipping the X and the Y directions. Additionally, we could look at how multi-axis sequential compares to multi-axis simultaneous. Are there interactions between those different axes that are important in contributing significantly enough to fatigue? Is the sequential multi-axial test that we perform on a shaker table going to represent the real life excitations that a part might see when it's out in the field, under the hood, or in service? So these are some different comparisons that we can take advantage of virtually when we look at all the different possibilities inside of DesignLife. And with that, I just want to cover a quick summary, and that is to say that what we've seen in the demonstrations in the slides here is that nCode DesignLife can be used to perform vibration fatigue analysis on results from a wide variety of FE tools. The vibration loads can be single or multiple, and they can be described a number of different ways. Those ways are random PSDs, which is probably one of the more common ones, potentially sign on random, sign sweep, or sign dwell. The fatigue methodologies can use both the stress life and the strain life material definitions, and vibration fatigue methods can be extended to things like seam welds and spot welds.